start, I'd like to acknowledge that we are from the University of Alberta, which is located on Treaty 6 territory and the North Saskatchewan River territory of the Métis Nation of Alberta. And this is a traditional gathering place for many diverse Indigenous communities whose histories, languages, and cultures continue to influence our vibrant community. As we explore energy systems, we acknowledge the territories, communities, and peoples who've been essential partners in our research. We are truly grateful to have the opportunity to work, study, and live on this land. Now, we are from Future Energy Systems. Anyone heard of Future Energy Systems other than you? Because you know. And Carlo, obviously. So for those of you who don't know, Future Energy Systems is a research program at the University of Alberta, funded by the Canada First Research Excellence Grant. And we were funded to help Canada transition to a low net carbon energy economy. We focus on multidisciplinary research that develops the energy technologies of the near future, integrates them into today's infrastructure, and examines possible consequences for our society, economy, and environment. We also contribute to the development of solutions for the challenges presented by our current energy system. We have over 1,200 grad students and HQP, over 150 projects, and 200 profs, I believe, involved in the program. So as I mentioned, we are filming, and it is important to note that for the current and future viewers, the opinions expressed by the speaker are not necessarily those of the Edmonton Public Library, the University of Alberta, or Future Energy Systems. Now, I am going to pass it to you. Did you do an intro for yourself, or would you like me to introduce you?
You can go ahead.
Okay, so I would like to introduce, for those of you who don't know, Ula Suliman, a PhD student from the U of A, who is a PhD candidate in materials and chemical and materials engineering, where she conducts research. Is there a way to say this, or just all the letters? NRG-MATS lab?
NRG Maths.
NRG Maths, under the supervision of Dr. Shiva Mahojania. And she received her BEng in 2016, and her research interests include electrochemical processing and development of advanced electrocatalysis, I think I said it, for water electrolysis and hydrogen production. I'm going to pass it over to you.
Thank you so much. Thank you, Valerie, for the really nice introduction. So, good evening, everyone. Thank you so much for coming today. You know, it's a Wednesday. It's usually like nobody really wants to go out in the middle of the week. You know, it gets tough, you know, on Wednesdays, work gets to a high. So thank you so much for attending. So as Valerie's mentioned, my name is Ula Suliman, and today I'm going to be talking about electrosynthesis. It's not really a word that we hear every day. It's quite niche, but I hope that through this talk that you learn something about it. And then through our discussion later on that we share perspectives on this topic. All right, so I'm just going to start with discussing just a general overview behind the incentives of electrosynthesis, why the research on electrosynthesis exists, what we need for a sustainable future, and then we're going to get into the core of this topic, which is electrosynthesis. We'll talk a little bit about the applications of it, and then I'll wrap up with talking a little bit about my research and what we have moving forward. All right, so whenever we mention things that have to do with electro/something, we usually also have to mention the fact that we are living in a very tension, like there's some tension environmentally that usually has to come up. So I just wanted to say that, like, we definitely live in unprecedented times in terms of human consumption. And this happened because of industrialization. So specifically, like founding chemical fertilizers. So what that led to is that it led to a population growth because of an abundance of resources, right? And this also led to, the need, like the energy demand increased. So because of this increase in energy demand, we were able to get So because of this energy demand, we had to fulfill it by using fossil fuels. And we are very lucky to be, to have fossil fuels to fulfill that energy demand. This is a privilege that we as 20th and 21st century humans have been able to have that millennia of human beings have not been able to enjoy, right? But our actions as human beings usually have consequences. And whenever we bring up climate change, there's always a spectrum of opinions, there's always lots of debate on it. But what matters is that we have certain problems and we need to propose certain solutions. So in 2015, I believe it was 2015, I hope it was, there was a Paris Agreement that has been proposed. And this agreement mentioned that we should be keeping the global temperatures under 1.5 degrees Celsius above pre-industrial times, preferably. And they also gave us an upper limit of 2 degrees Celsius. Now, the thing is, as of 2025, we are at that lower limit. And things are starting to exponentially get worse and worse. And if you look at the very first GIF over there on the left-hand side, I think I can use the pointer over here to make things easier. A laser pointer. I tried using my own laser pointer, but it just disappeared into the screen. I discovered that today. So if you see over here, this is like a heat map that I got from the NASA website. And you can see that the effects of the increase in global atmospheric temperatures are becoming especially apparent in the past 10 years. So there's something that we got to do about it, considering the fact that we are at that lower limit. And while we're moving towards that upper limit, we have a lot of things happening. There is loss of plants, there's loss of habitat, there's loss of species, there's extreme heat. And this affects us in more than just environmental factors. We also have, it affects our social framework as human beings. It affects us in the sense of conflicts. And it affects us in the sense of seeking for resources in days of shortages. So the effect is and it becomes cascade. Things start to become a little bit more exponential in its its exasperation. And so with that being said, we have to always bring up the culprit of things that are happening. So greenhouse gases. This is a phrase that we have been hearing a lot, and that we've been dealing a lot, especially as researchers. So they usually pose as, or they pose as one of the main culprits behind climate change. And they operate by the greenhouse effect. The greenhouse effect is the reason why Venus as a planet is hotter than Mercury, although Mercury is closer to the sun. And so usually when we're talking about mitigating all of these climate disasters, those anthropogenic effects on climate, we always talk about how we can decrease our emission of these greenhouse gases. Now, if we're talking locally in Canada, the efforts towards that have been better than the rest of the world. Most of our greenhouse gases, especially carbon dioxide, they come from the industry or transport. And although we are not really the top emitters cumulative in the world, we do have one of the highest greenhouse gas emissions per capita. So us as human beings individually, us in Canada, we emit much more greenhouse gases on average than most people in the world. So with that being said, Canada has proposed a target. There's this aim to decrease the greenhouse gases to up to 45% below the 2005 levels. That's the threshold that's been proposed. And it's been going well so far. there is a decrease. There's an 8.5 decrease as far as I know. But if we want to reach that 2030 goal, there needs to be a 30% more decrease. So there's more work that needs to be done in that regard. Now, there's something that I really want to mention is that rising global temperatures means an increased energy demand. You can think of it as like a chain reaction. If global temperatures rise, the energy demand rises, and so that means we are burning more fuels, and then we are emitting more greenhouse gases, and then the temperature rises again, and the energy demand increases again and again and again. So it becomes a cascade effect that we need to address and that we need to find alternatives for. All right, so our dependence on fossil fuel. I think it's an undeniable fact that we use fossil fuels as our energy sources overwhelmingly, and not just in Canada, but all over the world. And it makes sense why we're doing so, because it's more accessible. It's easy to burn it, to extract the energy that we need from it. It's direct. All you need to do is just ignite it. There you have it. You have the energy for it. And also because it's the starting point for so much manufacturing. So like it is the source for so many sinks, whether it's on an industrial scale or on even a personal scale. Fossil fuels are so versatile. They're so energy dense. And they're so easy to access. So it makes sense why the supply for it in different sectors is quite dominant compared to anything else. But that also means that our energy sources are not as diverse as they should be. We usually forget the fact that fossil fuels are a depletable resource. And that means that one day they're going to run out. Maybe not for us, but think about the future that we are lending. So like there's future generation that we're giving this planet to. And then they have to deal with the fact that we're consuming stuff and not leaving much for them. And so that being said, in Canada, the movement towards renewable resources is good. There's it's a huge step forward. But still, like that dependence really speaks a lot. And that really shows itself when we're talking about the chemical manufacturing industry. So not only is like fossil fuels the source, like the beginning step for so much manufacturing, it actually is 95% of manufactured goods, as far as I know, are like they come from fossil fuels. But not only that, but like just 26 essential chemical compounds cover 75% of total industrial energy. And we're talking about 26 out of thousands or millions of chemicals out there, right? And honestly, I really love this graphic because it describes something like quite like human about this. If you notice here, there's lots of like methanol, propylene, ethylene, butane, toluene, like benzene, toluene, and xylene. So all of these stuff that are usually more geared towards manufacturing. But then there's that ammonia at the top that consumes so much energy and releases so much greenhouse gas emissions through its production. And it makes sense because we as human beings, we need to eat, we need food, and that is the main component of fertilizers. So it really shows that fossil fuels they're also linked to our survival as human beings. And so are we really linking our fate to something depletable? This is something that we need to be thinking about. All right, so with that being said, what does a sustainable future need? So if you ask this question to anybody in any different field, you're going to get a plethora of answers. There are so many perspectives that could be used for a sustainable future. But in the context of this talk, of our conversation today, I would say that what we need is clean energy and sustainable production. Now, in terms of clean energy, the first thing that people think about is renewable energy transition. You use like basically the energy sources that we know of: solar, wind, hydro. They're available. They're in nature. They're renewable. Well, the sun is always there, depending on the season, and that is the key word. It depends on the season. So the main issue and the main reason why the confidence towards that transition towards renewable energy is low is because of how seasonal renewable energy sources are, and how not very efficient the energy storage is. And so how could we approach that lack of efficiency, and how could we increase the dispatchability of renewable energy transition is by moving towards low carbon fuels. And this is where electrosynthesis plays a part, right? So if we could harness the energy that we get from renewable energy and store them in a medium like other fuels that we could use later sustainably, we could solve some issues with regard to storing the energy that we harness from nature, right? And in the context of sustainable production, we need, number one, sustainable products, things that don't leave a large carbon footprint when we use them. And also, we need to think about decarbonizing the production stream. So when we get to that final product that we're using a lot of resources and a lot of energy in the way that releases a lot of carbon-based waste. So we need to think about that as well. All right, so let's get into it. What is electrosynthesis? I'm sure it's like there might be some questions posing inside. What is electrosynthesis? This is the moment that we've been waiting for, defining the title of our conversation. So let's start with synthesis. So simply put, synthesis is putting chemical A, chemical B, combining them together. It gives you chemical C. That is the simplest definition of what synthesis is. But to make it a little bit more technical, it is an artificial combination of different reactants that give you a desired product. And traditional synthesis, or traditional chemical synthesis, is the heart of chemical engineering, where you mix different reactants together in a certain operating condition, and you get a certain product. And so there's a lot of optimization that gets into this. And in traditional synthesis, and in traditional chemical synthesis, we usually deal with quite intense conditions. You have high temperatures, depending on your synthesis, high pressures sometimes, which means that we are consuming a lot of energy. I'll give you a very easy example. So to produce hydrogen, most of hydrogen, about 96% of the hydrogen that we use in the industry, it comes from fossil fuels. And a popular method of producing hydrogen is steam methane reforming, which pretty much you're combining methane from natural gas with high pressure steam at high temperatures, high pressures, in the presence of other materials, and essentially you get hydrogen from it. But here, what's happening is that we're using a lot of energy. What if we electrify this process to decrease that energy demand? So as I've mentioned, if I want to produce hydrogen from natural gas, I need really high conditions, up to 700 degrees Celsius, up to 330 bars, right? So like the conditions are very, very intense. But if I want to split water to hydrogen and oxygen, ideally, in ideal situations, all you need is 1.23 volts. And industrially, what we usually look at is 1.8 volts to 2.5 volts. So you go from these intense conditions to something quite mild at lower temperatures. You know, we don't get all the way to 700. And you also get much higher efficiency because the waste is less, the energy loss is less. All right. So why does it matter? I've been talking about, like, mentioning all of this, but why does electrosynthesis matter? And I've mentioned it in the sustainability, the sustainable future slide, is that number one, the most important thing about electrosynthesis is chemical energy storage. And I've mentioned that if you want to use renewable energy, you need to store it. But storing it is quite a challenge unless you have a medium for it. And you could do that by storing them in molecules, in chemical bonds. And that is pretty much the premise of green hydrogen. You are using renewable energy, and then you're splitting water to hydrogen and oxygen, and then later on you're using that hydrogen as a clean net zero carbon fuel. So you're storing all of that energy within hydrogen. And I'm going to elaborate on that later. All right. The second important thing is decarbonization. So in so many processes, in so many manufacturing processes, you're going to, like, the production stream has lots of steps usually, and these steps involve, like, if you look at them, if something starts with fossil, like natural gas or methane as a starting point, you're going to notice that throughout the process, carbon dioxide finds a way out. It always finds a way out. Just, it's like, it's always a byproduct of some sort, right? And so we can provide a shortcut by using electrosynthesis. And later on, we can actually use electrosynthesis to utilize carbon dioxide. So we can transform carbon dioxide to other value-added products, right? And so what that does is that it reduces the waste that we have. It reduces the air pollution. It improves our environment. And also, we can control the selectivity of a certain reaction. So usually reactions, they produce different products, and usually one of them only is the one that we desire. And so electrosynthesis can give us an alternative of providing a more efficient, a more selective way to produce a certain product, so it reduces our waste. So essentially, we're looking at a process that is highly efficient, highly selective, less waste, less environmental impact, and more carbon dioxide utilization. So we're looking at more carbon neutral, low carbon technologies. All right. So where does electrosynthesis happen? It happens in an electrolyzer. Now, an electrolyzer, and I wish I brought an example with me over here, but just to use our imagination for a moment, the easiest version of an electrolyzer is you get two metal plates, you dip them into an electrolyte like a salt solution, and you connect those plates into a battery. You're going to start noticing that bubbles are forming on both of these plates. And you can do that experiment at home, but please use like a low voltage battery. So you could bring 2 spoons, dip them into salt water, connect them to a battery, and you're going to start seeing some bubbles forming on the surface. All right. So those plates, those metal plates, we call them electrodes. And these electrodes is where the magic happens. We usually, the electrolyte or that solution is the one that carries the reactants for our desired products. And the electrodes is where the magic happens. Now, there are so many different versions of electrolyzers. The one that I've put here is the water electrolyzer, because unfortunately I could not find GIFs for anything else. So this one was the most accessible. But as you see, this is our reactant, water, that comes into the electrolyzer, right? And then we have splitting of water on the surfaces of these electrodes, from which they get transferred to the collection tanks over here. All right. Now, what I've been mentioning electrode, and I've been trying to emphasize what an electrode is. So like as much as possible. because these electrodes are the heart of this electrolyzer. They work with a really, I would call it almost magic phenomenon that we call catalysis. And catalysis is honestly a beautiful concept. It's opened a lot of doors in different fields. Catalysis is the reason why we have an abundance of crops today. The most popular application of catalysis early on is the founding of ammonia, the commercializing of ammonia, right? So before I get into like the technicalities, I wanted to imagine combining nitrogen and hydrogen together. In normal conditions, would you get ammonia? Like if I get, you know, like a small bottle of hydrogen or like a small like tube of hydrogen and I light it on fire, it's going to burn into water vapor so quickly, although 79% of air is nitrogen. So we're not really going to get that ammonia on time, right? But what they found through the Haber-Bosch process is that if you put hydrogen and nitrogen in the same vessel at high temperature and high pressure, but in the presence of iron, it converts into ammonia, right? And so the iron, it presents its surface as that meeting ground for different reactants, for them to negotiate on better grounds, you know, and give us the products that we have. So as you see on this picture over here, you've got this really high hill, and then you've got that alternative route. So reactions usually need energy for them to start. We call that the activation energy. And what a catalyst does is that it gives the reaction an alternative energy pathway for it to proceed. So some reactions that take a very long time for them to go on, in the presence of the right material, the right catalyst, they become manifest. Like, for example, water electrolysis. I mean, like, no matter how much I heat up water in like on a stove, it's not going to turn into hydrogen and oxygen. But I can with the right catalyst. And catalysis is the concept that differentiates between an electrolyzer and a battery. They have the same things. They have electrodes, they have electrolytes, right? But a battery runs out after time because its electrodes get consumed, especially if we're looking at like our typical alkaline batteries, right? So the electrodes they're the ones that get consumed. They're the ones that react. But in an electrolyzer, they don't. They let the reactants do their thing on the electrode itself. So this is pretty much the concept of catalysis. And the thing about catalysis is that it's a bit more complex than it seems. You know, if I put just a huge block of iron and expect the reaction to proceed, it will at very slow rates because there's not much space for it to proceed. So what we do is we break it down to smaller and smaller and smaller particles. We increase the surface area because, unfortunately, catalysis only happens on the surface of the material. It only happens on the very first layer of atoms, and then the rest of them are hidden inside, chilling, doing nothing, right? And so to improve the performance, we usually, one of the main concepts of this phenomena is by reducing its size as much as possible so that we can increase its activity. I hope that you guys are following through so far. It's like all good. Yeah. All right. So why should we care about catalysis? Well, first of all, lower energy demand. So reactions that usually don't happen easily without anything, they start to happen. And this, just like I've mentioned, splitting water into hydrogen and oxygen, or getting ammonia from nitrogen and hydrogen. These are reactions that don't really happen without anything, but when you give them the right environment, they happen. The magic happens. The second thing is improved selectivity. Depending on how a catalyst is, depending on its shape, its structure, it pretty much gives us the right reactant, the right product that we need. So this is quite important. It also influences the durability and cost effectiveness. Think about it. You want a certain product. And so when you choose the right catalyst for it, you save energy, you get as much of the product that you want, you reduce waste. And so by choosing the right catalyst, you lower the operating cost of a certain reaction to go on. And now there are so many things that influence the catalysts and how they give us the results that we want. So for example, the structure of carbon monoxide, and just based on the different, these are all cobalt or cobalt oxide, but depending on the ratio depending on the structure of cobalt oxide, you get, number one, different yields of the products and also different ratios of the product. So it all, depending on what your structure is, you're going to get a different product at the end. And also, what really matters is the environment that you're putting it in. So the pH of your reactant matters, the temperature, the pH, of your environment matters, the temperature matters, all of these factors matter. And so there's a lot of things to consider when we're designing the perfect, and I put that in quotation marks because it's never perfect, especially if you're working in this field, it's never perfect. So there's lots of trade-offs that we need to consider. I could have a catalyst that's very active, but then if I put it in an electrolyte, it starts to fall off, and I lose my material. It could be quite selective, but its activity is quite low. So there's lots of things to consider when we're designing a catalyst. And also, we should be considering what kind of materials are we choosing. So if you're choosing an abundant material versus a rare noble material, like for example, platinum or iridium, you're going to have to think about how you're going to trade their very high activity versus their cost, which also means that you need to think about what happens when you scale up. Lots of time when we are designing catalysts in our labs, they have really good performance, but then when you put them in an electrolyzer, an industrial grade electrolyzer, they just don't work, right? And so you have to figure out why that happens. And so there's lots of factors that need to be considered when you're designing it. All right, so I've talked a lot about catalysts and how they're relevant in the context of electrosynthesis. But truly, it is the secret behind having that dual energy product pathway. And this is where we go back to hydrogen, right? So I've talked about how we could use electrosynthesis to store renewable energy in low carbon fuels. Well, hydrogen is a low carbon fuel. In fact, it is so energetic. It's multiple times more energetic than gasoline. You're storing that renewable energy in these chemical compounds, but at the same time, you could use them to produce other chemical compounds. So for example, this nice schematic shows us how through reducing carbon dioxide electrochemically, so if we want to electrosynthesize stuff by using carbon dioxide as our starting point, there's always a pathway towards, for example, synthesizing plastic, or synthesizing renewable natural gas, alcohols, or even different kinds of fuels. So we can incorporate it in these synthesis routes, right, to get our final products that we desire. And at the same time, electrosynthesis could pose itself as an alternative method of producing hydrogen. So traditional water electrolysis involves splitting water to hydrogen and oxygen. But then oxygen is abundant. So it's kind of like, how can we valorize that area? So we could replace it with another oxidation reaction, right? That gives us other valuable products, right, at more energy efficient rates. So for example, I'm going to talk a little bit about this when we're discussing my research spotlight. We could use, for example, instead of oxygen evolution, we could use glycerol oxidation, right? So glycerol, we could produce other products, for example, like formic acid from glycerol oxidation, and produce hydrogen. Both of them are valuable instead of just having one half of our electrolyzer being valuable and the other one is just oxygen, right? So, electrosynthesis in action. What are the applications of electrosynthesis? Usually when we talk about electrosynthesis, the first thing that comes to mind to lots and lots of researchers is carbon dioxide reduction. And deservingly so, because carbon dioxide reduction is quite versatile, number one. Number two, it's a carbon neutral method of producing chemicals. So it contributes a lot to a circular economy. You have carbon dioxide as a byproduct of so many processes. You put it in an electrolyzer and you reduce it, and then it gives you other commodity chemicals, like for example, methane or ethanol or ethylene. Now the thing is, we need to figure out a way to be able to compete with natural gas when it comes to carbon dioxide reduction. Because like you can already like harness methane from natural gas, right? So there always has to be a way for us to think about how we could market carbon dioxide reduction and electrosynthesis through carbon dioxide reduction as a profitable technique, right? So here, like carbon dioxide utilization poses itself as a very important application. Another thing is waste valorization. So we could use electrosynthesis in the case of water treatment, right? You've got a lot of organic waste, especially that we could valorize and turn into value-added products, or also in biomass. So for example, like trees, right? So like tree waste, for example, or forestry waste, for example. And I'm going to talk a little bit about that later on as well. And also in sustainable production. I love bringing up ammonia as an example because of how essential it is and how relatable it makes things, you know, like whenever we listen about, you know, food and like needing fertilizers for us to sustain our lives, it also brings about the question of how are we, you know, planning to transition to a sustainable production. Yes.
So when we're talking about electrosynthesis, often from what I've heard, people are thinking more that hydrogen side. Are we seeing industries already taking it into these areas, or is this new? We're not there industrially yet, or kind of where does this live?
It's a new technology.
Okay.
Like it's relatively new. There's been movements, there's been startups towards using electrosynthesis, but it's still it's a baby like field, okay, right? And that is exciting because that means there's lots of progress that can be made in that field, especially because industries like the industrial sector is quite reluctant towards transitioning towards these technologies, and I will discuss that later on as well, because if you want to transition to like something like electrosynthesis, you have to have the infrastructure for it. And the infrastructure that we have today is more so like compatible with traditional synthesis, right? So there's that question on how could we implement this in our existing systems? Awesome. Right? I hope that answered your question. All right. So what are our challenges in terms of research? Well, there's quite a bunch. It's been fun doing research in this, and you could see that with my dark eye circles. So number one, how can we balance between efficiency and cost? Now, electrosynthesis is exciting and everything, but the best catalysts usually tend to be rare noble metals, right? Things like platinum or gold or even iridium. If you want to get a perspective about this, iridium, we get like about 6 to 7 tons of production of iridium per year. So imagine if we want to commercialize this, how much iridium are we going to use, right? And so that means we need to find alternatives, right? We need to find abundant alternative catalysts. They're cheap, but the efficiency is still not up there to what we need, right? So there's things that we need to think of. How are we going to balance between the efficiency of the process, the activity of catalyzing everything versus the cost? And also, since we're talking about sustainable production, we're talking about a sustainable transition, we need to think about how we consume the operating parts of this electrolyzer, right? If we want things to be sustainable, but at the same time we're using a rare depleting metal as our source, that kind of defeats the purpose, right? Another thing that usually is challenging is balancing catalyst performance parameters. And I've mentioned this earlier in the trade-offs. Like a catalyst could be very, very active, but then its stability is very depressing. Or it could have both, but then it does not give you the product that you want, right? So you have to balance between different parameters, and you don't really get something that's perfect. You get something that is feasible enough for you to apply it, but the perfect catalyst does not really exist, right? And then again, oops, where is it? Okay. And then we also have upscaling. How can we carry out what we have in the lab to the industry, right? There's lots and lots of research on different catalysts, different electrosynthesizers, right? But are they practical? That is the question that we need to ask ourselves. Are these practical? Like you could have something that works very well inside a lab, but then if you want to apply it in an actual electrolyzer, it doesn't work. And so you have to find a solution for that, because you need to not just consider the operation of the catalyst itself. You have startup, right? You have shutdown procedures. Instead of like in labs, we usually test them for like, hundreds, tens of hours, dozens of hours, hundreds of hours. But in real life, you want to operate this for thousands of hours, right? Or tens of thousands of hours. And so how can you extend that operation from the lab to the industry? And also how we could integrate that into existing infrastructure. That is an important thing to ask ourselves. All right. So coming to my research, what do I do? So in the past few years, I've been working a lot with catalysts. So my research mainly focuses on designing catalysts, and I focus on nanostructuring and on optimizing the support. And I'm going to talk about what a support is coming up, right? And there's lots of parameters to improve. And what I focus on mainly is the conductivity of a catalyst and the overall durability, like how active, how selective, but also how stable it is. And all of this is to essentially make electrosynthesis more practical, right? My story. So there's lots and lots of electrosynthesis processes. It's almost becoming an umbrella term right now. But there is one that I worked on before, and some members have been working on as well. It's called glycerol electrooxidation. So if you don't know what glycerol is, I'm pretty sure you've heard of glycerin soap bars, but they've been quite popular when I was young. Glycerin soap bars, glycerin lotions, because it's quite moisturizing. So the cosmetic industry is very, very familiar with this one. Now, glycerol usually comes out as a waste of biodiesel production. Biodiesel is an alternative green fuel that comes from biomass. And glycerol is usually a waste product. So, and literally for every 100 kilograms of biodiesel, there's about 10 kilograms of glycerol being produced. Now, the main issue with glycerol, it's very popular in the cosmetic industry, but not everywhere else. So there's a lot of supply, but not much demand, which makes it a low value product. And so if we want to make use of it, we either dump it, not so much fun, or give it to the cosmetic industry and tell them to deal with it, or we could turn it into valuable products like lactic acid, formic acid, right? So products that we could use and in which we could store energy, right? And also another thing, it's an energy efficient alternative to oxygen production. So I mentioned earlier that if you want to produce hydrogen, what usually is done is that you split water to hydrogen and oxygen, but you could instead inject glycerol into the oxygen side and oxidize it to value-added products, right? And it does that at ideally, the lowest value is 0.69 volts to transform it completely to formic acid. Compare that to, for example, if you want to split water to hydrogen and oxygen, you will need 1.23 volts, right? So you save like more than half a volt over there of energy, right? Yes.
Sorry, it's me again. So often when we talk about hydrogen, some of the concerns we hear are that it uses water. And if you're in areas that have limited water, that becomes a concern. So this would completely replace the water in...
It will reduce it.
Okay.
Yeah. So it will reduce the amount of water that you're using because you're replacing some of that water with the glycerol, right? Awesome. But that's also like, something that's very important for us to know is that fresh water is like, it's not an available resource, right? And so there's also the question of how could we use, for example, seawater or wastewater? This is a method that we could use it for. And like we could use electrosynthesis for treating like wastewater, and also we could couple it with hydrogen production, right? So that's the magic. That's the magic behind electrosynthesis. Now, how do I do this? How do I approach this problem? I do that by designing abundant metal-based catalysts. So things like titanium and copper. If you want like just a rundown of these metals, titanium is the second most abundant transition metal, not the most abundant metal because you have lots of sodium in the sea, right? But it's the second most abundant transition metal. So this is something that I work with. So I either design catalysts that use abundant metals, or there's a strategy. So I've mentioned before that the best performing catalysts usually tend to come from rare metals, right? And so one way of sustainably using those is by reducing the size of the catalyst so much that we go to the single atom. So by using single atom catalysis, we are saving up material, but also we are trying our best to maximize performance. So I've mentioned before that catalysis is a surface process. Everything happens on the surface. It always happens on the outermost layer of atoms. So imagine this nanoparticle. There's lots of atoms inside that do nothing. But if we reduce the size to a single atom and then we plant them all over a supporting material, you've got like small powerhouses like distributed all over your material, and then it makes catalysis more efficient. That is the hypothesis. That is what we're trying to work on. And now the star of the show in my research is titanium dioxide. It's an amazing material. I love it so much that you can see the love in my dark eye circles. So I use it as a support. So a support is a material that keeps the catalyst in place. So let's imagine that you have a reactor and you're allowing a flow of hydrogen inside the reactor and nitrogen inside of the reactor, and you have very fine particles of catalyst all over. without any support, well, they're going to fly, right? When we think of oxides like sand, we don't think about conduction, right? Or electric conduction specifically. But titanium dioxide is an exciting one because it's semiconductor, so it conducts a little bit of electricity. And the nice thing about it is that you could tune that conductivity, you could change it somehow with different techniques. And it's very, very, very stable, right? That stability, it makes it so attractive. Everybody's trying to use it somehow for their catalysts and because of its other properties as well. And also because depending on what morphology, depending on what structure you have, you get different properties every single time. So it's quite versatile. But it has a problem. Well, it's semi-conductive. It's not very conductive. It's conductive, but it's not enough. Like we're dealing with electrosynthesis. That electro part is very important. And so that means we need to do something about that semiconductive behavior. We need to improve it. Because believe it or not, in an electrolyzer, if your electrodes are not conductive enough, it's not going to work very well. So your catalysis is going to go in vain because of that. So my research mainly focuses on engineering the titanium dioxide for increased conductivity and to make its activity much, much more than it should be, right? So where do we go from here? Well, hopefully we see that in the coming few years, we have a transition towards a more carbon neutral synthesis world, right? If we find a way to store our renewable energy into like chemical bonds or just storing renewable energy in general in a very efficient way so that we are able to like transport it properly as well, that would be great. So I've put this schematic over here because I just wanted to show how versatile it is, right? It's not like the end-all solution. There's always like different routes, and I tried to include some of them over here. But I wanted to show how like electrosynthesis could contribute in improving the circular economy that we're trying to go for. All right, but there are challenges beyond the lab. So in terms of research, we can do much, but then outside of research, we need like collaboration on all fronts. We need industrial and policy collaboration. We need collaboration globally between scientists, policymakers, and also in terms of infrastructure as well. Luckily, in Canada, 80% of the grid in Canada, 80% of the grid, I believe, is non-emitting. So that's good news. But then what about the rest of the world, right? Like, it's true that we are contributing our share in greenhouse gas emissions, but we need to extend our science, our policy, our awareness. We need to extend that, which also brings about the need for public awareness. We need to educate people more, which is what we're trying to do over here, right? And so this needs collaboration between all of us, all sides of society as well. Now, I want to close this off by saying that electricity is the cleanest reagent we have if we learn to control it, right? And this is exactly what we're trying to do through our research. And hopefully we are able to one day in the most efficient way possible. I feel like efficient is the star keyword of this presentation. Like if you put this presentation somewhere, the keywords would be efficiency. All right, I just want to give a moment to acknowledge our funders, and I would love to thank my supervisors, Dr. Shiva Mahajania and Dr. Jing Liu, for their support. And thank you all for attending, and I am open to any questions. Thank you so much.
amazing. You did a great job.
Thank you.
She was very nervous before. But you didn't show any nerves. Discussion, questions. What do you guys want to know? Yeah, Neil.
Anna.
So in terms of energy input for traditional synthesis and electrosynthesis, what's the scale of comparison? As in, how much does electrosynthesis mitigate from traditional?
So electrosynthesis in general is more efficient because you have less heat loss, less energy loss in terms of heat. You could have a more distributed production because you could have modular setups, you know. So there's that portability factor that also helps with that. And also they tend to be more compact, right? So you're using less space. So there's the energy conservation tends to be a little bit more with electrolyzers and electrosynthesizers in general.
And just a follow-up on
Yep.
that. So you mentioned that it's modular.
Yeah.
And the current challenge right now is infrastructure gap.
Yeah.
So do you think modular retrofits are possible, or is that still miles away?
I would say that there is a possibility for it, especially here in Alberta, because there's lots of expertise in terms of chemical industry. So if we're talking about Alberta alone, infrastructure for that exists, and also expertise and personnel for that exists as well. So implementing such setups into existing factories or existing plants, it is possible. There will definitely be some changes, especially in terms of transport or storage. But in terms of synthesis itself, it's easier here in Alberta than the rest, but there's still potential for it across the country. That's it. Thanks. Any questions?
So if you mentioned that energy storage is a problem,
Yeah.
right? Why can't we just store it in batteries?
So the issue with batteries, the main issue with batteries is that, as I've mentioned before, is that they run out of material. So the amount of time in which you can store energy in a battery, there's always an expiration date, right? And that expiration date is short. So that's exactly what happens. For example, when you I'll give you an example. I have this small food weighing scale, and the last time I changed the lithium ion battery inside of it 2 months ago, and I'll have to change it again. So because of the nature of batteries, they run out of the material that helps in conserving that energy. With electrosynthesis and with storing them in chemical bonds, you can store that for a longer period of time, as long as you're not using the chemical. And at the same time, we also have the circular economy factor. So for example, if we're using low carbon fuels, they still will produce carbon dioxide, not as much as fossil fuels, but you can still bring back that carbon dioxide, put it into an electrosynthesizer, and produce more low carbon fuels. So it's the process ends up being a circle if we could improve direct air capture. So, and I would say that's one of the main bottlenecks with carbon dioxide conversion, with electrosynthesis using carbon dioxide, is that the technologies for direct air capture of carbon dioxide are not mature enough for it to be for us to have a full-scale commercialization. So if we figure that out, then we have a long shot with electrosynthesis.
You talk about batteries running out of materials. How often do you have to replace the catalysts in?
It depends on the stability of the catalyst. So some catalysts are quite stable. They would stay for I know some electrolyzers, I think a year-ish before you start to replacing some catalyst. But if you have and that's why we usually try to optimize stability a lot, because you want it to stay for a very long time. You want the operation for a very long time, and also because you want to use that material for a very long time, because some of it is rare material, right? Which also brings about conversation about the recyclability of these catalysts later on, right? And so these are also like factors to consider as well in like designing those systems.
Yes. So in the beginning, you talked about hydrogen production and the difference between producing hydrogen from natural gas versus producing hydrogen from electrolysis.
Yeah.
So what's the most efficient way to make hydrogen? And if it's scaled, can it replace, can that hydrogen replace fossil fuels as a cleaner alternative?
All right, so replacing fossil fuels with something else, to be honest, full replacement is not something that I would generally support because like they exist, right? And we can use them. The topic here is how could we use them sustainably, right? And also because if fossil fuels are a depleting resource, and then replacing it with something else, and we still don't know the long-term effects of it, that wouldn't be the best strategy, right? So the best way to approach this is to think about diversifying our energy sources. That is what matters the most at this point, diversifying our energy sources and trying to use our existing energy sources sustainably. I think that is what matters the most. Now, in terms of efficiency, electrolyzers are more efficient than combustion-based processes. So anything that involves combustion, electrolyzers or fuel cells, which are like the reverse of them, they're more efficient because like there is less loss of byproducts, there's less heat loss as well. So they have like on average like a higher efficiency of about 15 to 20% higher efficiency.
I can add something onto that.
Yep.
So in terms of like replacing fossil fuels with hydrogen, I would say you have to be more directed on what exactly the application that you're using fossil fuels for that you can replace with hydrogen.
Yeah.
So when you think about it, a hydrogen fuel cell, what it does is it takes the energy that's stored in the hydrogen bonds and produces electricity. So just based off of that, you could think of, okay, what are all the things that I use electricity for? If I'm using fossil fuels to make that electricity, maybe I could just start replacing it with hydrogen.
Yeah.
So things like, for example, you've heard of hydrogen cars. I mean, the Edmonton Airport, I think they bought 3 hydrogen cars last year or something. And really, what is a hydrogen car? It's an electric car, but instead of using batteries, it will use a hydrogen fuel cell. You think about the energy grid here in Alberta and even in Saskatchewan is very, very carbon intensive compared to especially other provinces like Quebec, which uses a lot of hydrogen. So we can produce hydrogen as long as it's in a clean way, so using a renewable resource, we can displace some of the fossil fuels used in those things.
Yeah.
So I guess we'd be more directed at what exact applications you want to use it for.
Yeah. For example, like one of the most popular applications for like that hydrogen transition is like large vehicles, so trucks, buses, because like you could, like there's more space for them for us to operate like with hydrogen storage, right? So usually like hydrogen transition usually targets those, heavy duty applications like heavy vehicles or even the heavy industry like steel production, for example. But in terms of like a widespread like replacement, it's kind of like we also have to think about the feasibility of it, and we also need to think about the infrastructure that we have that is being put, because like natural gas for a very long time has been like promoted as a cleaner fossil fuel. So we also need to think about how we could integrate all of these different aspects and all these different like energy sources together. That is what matters the most, rather than replacing one thing with the other, because like replacement is not always the answer. Like when we have only one thing to depend on, it makes life a little bit harder, right?
If you think about it, a place where I guess hydrogen cars are more popular is California, and I think that they only have a handful of hydrogen fueling stations there. Germany has quite a few, but the infrastructure is not there for a widespread. And it's just my opinion. I think it's going to be doubtful that it will really take off in a way that's going to be very meaningful.
Yeah.
I expect there to be local uses, like for example, Germany has its own little infrastructure, California has its own little infrastructure, but for widespread use, I think it's not there yet.
Yeah.
The cost to make a hydrogen fueling station is significantly higher than the cost of making a normal gas station or even just an electric, place to charge your car. So I think that we're not there yet. Maybe if I got this question in the next 10, 15 years, I'll have a different answer. But that's the goal with research,
Yeah.
Today it's not feasible, but who knows what happens in 10 years, 15 years from now.
And there's also like the concept of like, when it comes to the infrastructure, it also depends on like public awareness. So people are scared of hydrogen. Like there's this cloud of doubt amongst like the general public. They're like, oh my God, a hydrogen station, what if it blows up? So that's like, that's real, that's, and that is like, so there's awareness, like there's public awareness that needs to be, addressed in that regard. And just like you've mentioned, there's not many like fueling stations. I think there's a good bunch in like Montreal and Vancouver, but then the rest of Canada, there's still a long way to go. Yeah.
Absolutely. Yeah.
Yeah, sorry. Can you go back to like the game slide earlier? Yeah.
This one?
I think I was talking to your supervisor like last time because we were filming as well.
Yeah.
But like, is there any like I'm not so sure if like correct me if I'm wrong as well. Is there like any like way, because we know titanium and iridium are like really expensive metals. Have you like looked into like coupling it with any conductive support materials to enhance
So
something visible? I'm not
yeah.
really knowledgeable.
No, that's fine. That's actually like one of the key aspects of my research, actually. So in electrocatalysts, usually like people popularly use powdered catalysts. And one of the main issues with powdered catalysts is that if you want to stabilize them, you kind of like have to mix them with binders. And these binders are not very conductive, so they reduce the like performance of these powdered catalysts. So what I do in my research is that I synthesize binder-free catalysts. So I grow my support over a metal foil. So like they're directly bound to the metal foil, which is the conductive support, basically. Yeah. So there's conductive support to the support material.
Thank you.
No worries.
Any last questions or discussions that anyone would like to have? This is your space.
It's like if you're shy, you can also send me an email.
We'll be around for a few minutes at the end if you want to come up and
Yes,
talk.
100%.
But can we give another round of applause? Well, thank you all for coming.
Thank
If
you.
you are interested in learning more about future energy systems and the talks that we host monthly, you can sign up for the newsletter. There's a link there on the door. There's some surveys if you'd like to fill them out. We are not back until the winter semester, so we've got talks from January to June. Talks include forever chemicals, sustainable design, working with Indigenous communities, so quite a range of topics in the winter, so we hope you will come back and join us again. And if you are interested in learning more about energy storage and batteries, we're hosting a talk on campus on a date that Carla made a post about it today, or agreed to a post about it today. October 22nd at 4 o'clock, University Commons. It's part of the sustainability lecture series. If you want to come learn about batteries, you can come learn on campus if you are from campus. And if you want to, can I ask who is a U of A student here? Is it most? Okay, some humans. Okay, if you are a U of A student and you would like opportunities like this to do public lectures or to engage with community, come talk to me because we offer research training and lots of opportunities for these kinds of events. But thank you all for coming, and feel free to come up and ask
Thank you so
questions.
much.